All right, this is problem 5-127 on page 313. And there's a general statement about what we're supposed to do. Use the theorem of three moments to determine the reactions at all supports and draw the complete shear force or shearing force and bending moment diagrams. Indicate the maximum shearing force and bending moment for each beam. So we'll do that. And I've made a solution here. I hope it's right. I think it's right. I've got erase marks, so I think I've corrected it. But I don't recall. It's been a while since I looked at this one, so let's see what happens. So if I make mistakes and you see something along the way, please do speak up and say something. I'm not 100% convinced that I worked this one properly. Let's see. Anyway, there's three supports, so this is a statically indeterminate problem. There's no moment support, just force supports. And this is point B, just to make things consistent. We got A, B, C, and D there. There's a meter over to the 25 kilonewton load, and then the supports are beneath the ends of a distributed load, which is 20 kilonewtons per meter, and the entire length here is 1.2 meters. The length from A to C is 2 meters, and so we could say there's a meter length there as well. Okay, so what I did is I started off by writing down the theorem of three moments, or the equation for it. I just wrote down the whole thing, which I think is equation 5-9, isn't it? What equation is that?
Yeah, it's 5-9.
Is it 5-9? Okay. Because there are three there, and we just need one that can deal with both a distributed load and a point load. So we've got to have, I think that's the only one we can use, in fact. Now, in the equation, they have the moment at B. Okay. The thing is that in my case, I'm going to use, you could actually cut the beam either here or here in the most general sense, right? But remember, in the theorem of three moments, we always end up cutting the beam somewhere, right? I can't cut it here. I can't select B to cut it because the equations we have won't work for it, right? The theorem of three moments equation has to have a distributed load along an entire section. So I have to choose to cut it at C. So that's why I had to take the moment at C here, and I couldn't do it at B. If we had something that was a little more general, an equation that was more general, we could have cut it wherever we want. But we don't. So L1 plus L2. And of course, that's going to make this L1 over here is L2, so we can define those clearly. Then plus the moment at D times L2. That's just the left-hand side of the equation so far. Let's start looking at it to see what we can get rid of from the very beginning. At A, there is no moment, right? At D, there is no moment. At C, there is a moment within the beam. We just don't know what it is. So these two terms are going to go away. Now, going over to the right-hand side of the equation, it looks like this. There's a negative summation PIAI over L1 times L1 squared minus AI squared. Remember, in the equation, that parenthesis is missing. If you're watching the video, you may want to make sure it's in your book. And then there's another term. Now, this term is for loads, point loads in the A section, or the 1 section, if you will. The second term is for point loads in the 2 section. Of course, we're not going to have any of those, but I'll go ahead and write it down. BI over L2 times L2 squared minus BI squared. Okay, and that's not all of it, right? There's still more to it, but let's deal with the point load parts first. There is a point load in section 1. It's this 25 kilonewton load. But there is no point load in the next section. Okay? So what I'm going to do is just go ahead and cross that term off too and realize I don't need it at this point. There are two more terms, and each one is for distributed loads in section 1 and for distributed loads in section 2. Okay, now we don't have a distributed load in section 1, so I get to cross this term off. Okay? So I wrote down the big long equation so I can simplify it and you can see what we get. Let me use the power of the whiteboard. That's not going to help me much. Never mind. Tell you what, we'll just go ahead and plug in numbers to the terms that survive that initial analysis and see what happens. So the only unknown in this equation is what? Well, we know the location of the point load. right? We know how big the point load is. We know L1, we know AI, that's easy because there's just one point load in section 1. We know what the distributed load is in section 2. We know how long section 2 is, so that term's easy. So basically the right-hand side is just numbers, right? That's the way this equation always works out. You've got the right-hand side of numbers. Most of the time you're just looking for one moment. It's usually the moment in the middle of the beam that you don't know. So 99 times out of 100, that's the part that you don't know. Of course, the problem could be set up where you're given that and don't know a moment at the end, but that's how this one comes out most times. So let's figure out the, let's just plug numbers in, that'll be the easiest to do. So 2 MC multiplied by L1 plus L2, that's 2 meters plus 1.2 meters, so that's 3.2 meters for L1 plus L2, and then we need our equal sign because we're to that point. We don't really need the summation because we've only got one load, and that's the 25 kilonewton load, so 25 kilonewtons multiplied by the distance. Now, you got to be careful. There's a figure above the long equation 5.9. Some of this I'm saying for the value for the camera, but there's a figure there, and you got to note that the position of the loads are measured basically like this. Okay, so for A, it's measured from the left-hand side. For section 2, B is measured from the right-hand side. Okay, of course, we don't have one in this case, but you need to be careful about that and know how to measure the position of the loads. So this is just 1 meter, and that's that term right there, AI, over L1, which is 2 meters, and then L1 squared. Well, L1 is 2 meters, as we said, has to be squared, minus AI, which is 1 meter squared, this particular load. And that takes care of this term, right? We filled in everything for that term. And I've got parentheses around it, so that should be good. There's nothing here, and then all we need is the distributed load. I'm out of space on the camera, so let me just put it below. Minus W2, that's the distributed load of 20 kilonewtons per meter, multiplied by L2 cubed. L2 is 1.2 meters, and then divided by 2. Okay. It's always good to check our units and see what's going on here, make sure we haven't made a mistake. We've got meters canceling here, so we'll have kilonewtons meters squared. The next term we'd have, let's see, kilonewton meters squared, because one of the meters would cancel, so it'd be kilonewton meters squared. On the left-hand side, if the moment is in kilonewton meters, then times meters would be kilonewton meters squared. So that would work out. So the moment will end up being in kilonewton meters, which is what we would hope. What I did is I solved this and found that the moment at C then comes out to about negative 7.2094 kilonewton meters. Is that what you guys are getting as well? No. Get it right now. Oh, I made a mistake, guys. I'm sorry. See this 4 here and this 2 here? That should be a 4. And so we need a 4 here also. My mistake. I just copied it down wrong. Got it right on my sheet and I wrote it wrong on the board. Let's see. 4 minus 1 is 3. So 3 halves of 25 would be 37.5. Now 1.2 cubed is going to slow me down.
So that's 7.2094.
Verified? Okay. All right, so there's our moment at C. All right, so now we can break up this beam into 2 parts. Let's work with, let's see, which one did I take first? I worked with the left-hand side, that's what I usually do. So I worked with the left-hand side first. At the reaction at A, you got the point load of 25 kilonewtons. And of course, it doesn't really matter if you talk about the reaction at C being here. It's not going to cause a moment about point C anyway, so I'm not worried about it. But there is a moment, and remember, this is the part that's confusing. I always use the sign convention, so I draw the moment at C in the positive direction. Now, this is not the positive because it's counterclockwise. It's positive because it's on the right-hand side. And so the way this works is you got shear positive in these directions on the right and left respectively, and then moments positive in these directions, counterclockwise on the right, clockwise on the left. Those are the positive directions. So I know that my moment came out negative. I'm going to plug a negative number into the equation, okay? So I think we can get rid of all of this. Let me just make a note that the moment at C we know now is negative 7.2094 kilonewton meters. So that way we don't forget it. Then I've got this space to work in. Okay, so now working with this free body diagram, what do we have? Well, let's sum moments about C taking counterclockwise as the positive direction. Now this counterclockwise direction being positive has nothing to do with the right-hand side being positive counterclockwise, okay? They're two different things. So I'm taking counterclockwise positive, so the way that MC is drawn is in the positive direction. It's also in the positive counterclockwise direction, so I'll just write MC. Okay, and now all of my signs should end up being consistent. So then the 25 kilonewton load will cause well here, let me write the reaction first. The reaction at A will cause a negative moment. It has a 2 meter moment arm, and then the 25 kilonewton load has a 1 meter arm, and of course is in the positive, or causes moment in the positive direction. Okay, it causes a counterclockwise moment. So from this, since we know MC, in fact, let me just do it this way. MC, we know, is negative 7.2094 kilonewton meters. Then we can solve for the reaction at A. So you just plug it in, it's straightforward. The reaction at A then comes out to about 8.8953 kilonewtons. And now I get a nice sanity check because it seems to me that the reaction at A should be up. That makes sense. So if I'd got a negative number, I would look back through my math and see if maybe I made a mistake somewhere. But I feel fairly comfortable with that. So that's the first free body diagram. That's the left-hand side. Now let's do the right-hand side of the support where we've calculated the moment in the beam. So the right-hand side free body diagram, we'd have the reaction at D, consistent, use a capital D. We'd have the distributed load along that entire length from C to D. And now we can, we've also got the moment at C. Okay. Notice I've drawn the moment at C according to my sign convention of a segment. Okay. So that's the positive direction. So now, if I sum moments about C taking counterclockwise as positive, wait, I thought you just said that clockwise is positive. No, I'm summing moments, positive counterclockwise. The moment at C would be positive if it was in this direction, right? But I have to observe the sign convention, and so it's going to be a negative. Basically what I'll do is I'll plug in minus MC, because the direction I've drawn here is against my positive, right? And then I'll plug in a negative for that. The negatives will cancel, and I'll get a positive term here. Okay, and I forgot. It's better sum up to 0, right? So anyway, the moment, negative of the moment at C, and it looks like I have made a mistake in my my solution here. So let's see, because when I plugged in MC, I didn't attach that negative sign. Let's find out what happens. So we'll run through the numbers and see what happens, okay? Anyway, so we're going to have RD multiplied by 1.2 meters. And let's see, well, we've also got the distributed load. The distributed load is going to cause a clockwise moment about C, so that's a negative thing. So minus 20 kilonewtons per meter multiplied by 1.2 meters worth. I'm out of room on the video camera, so let me put one more term multiplied here, which would be the centroid location of that resultant, right? Because we're going to have a resultant of this whole thing. That's what we just computed, the 20 kilonewtons times 1.2 meters. So 0.6 meters from C is where it would be located. So now we can solve for RD, and here I'll have to rely on you guys to give me the number because, no, I did do it right. I'm missing a negative sign here, but I did take, or did I? I don't know. I'll let you guys solve for it. So plug in a negative 7.2094 and solve for RD. What would that do? Well, this term would be positive, When you move it to the other side, you get negative 7.2094, right? That would be that term. This term would go to the other side positive, so plus 20 times 1.2 times 0.6, and then divide by the factor on RD 1.2. And actually, that's exactly what I did. So
5.99.
yeah, that's what I got, 5.9922 kilonewtons. And I just forgot to put that negative sign right there in my equation, so I'll stick that in. But I did observe the sign convention, so that's okay. All right, so that takes care of the reactions. The reaction at A was 8.8953 kilonewtons. Don't care about that so much anymore. The reaction at D then is 5.9922 kilonewtons. And now we can sum forces and find the reaction at C. So summing forces in the Y direction is straightforward. I won't write that out. You guys know that by now. I've got it on the page here in case you need it. I got 34 some odd, so let me just write it in here. I got 34.1125 kilonewtons. If you guys wouldn't mind, add the 3 reactions, okay? And see how that compares to 25 kilonewtons plus 20 times 1.2. Should be the same.
Got it. 0.
It's 0, okay, so that works, all right. So we verified the reactions, or we calculated the reactions, excuse me. And so now you could check this because you could sum moments at A, for example, and find out if the moment of the point force, the distributed load, and the 2 reactions comes out to 0. I did that and it does. So if you want to see that, I can go through it, but it's here on the sheet. Okay, so the next thing to do then is to make shear and moment diagrams. And from here on out, it's pretty straightforward. Really, the theory of 3 moments is the long, hard part we're not used to yet. So let's see. Shear in kilonewtons. Okay, it's pretty obvious the shear is going to be 8.8953 as we cut to the right until we get to the 25 kilonewton load. So let's see if this is A then. We'll go up to, pull that down a little bit for scale, 8.8953. Then we'll go to B, where we've got to move down by 25 kilonewtons. So if you take 25 away from 8.8953, you'll find that you go down to negative 16.1047. Okay, and that will be constant until you get to C. And let's see, wait a second. Oh yeah, because of the 34. So I have to add 34 to a negative 16.1047. And so that would take me up to 18.0078, probably 18 kilonewtons, close enough. And then the distributed load basically just determines the slope, and it doesn't go down to 0. So the distributed load determines the slope, and so 20 kilonewtons per meter times 1.2 meters gives me a change of 24 kilonewtons, and actually it does go below because we're at 18, so it has to go below. So that delta is 24. That brings us down to negative 5.9922, which then brings us back up to the axis, so that works. Okay, so there's my shear diagram. And I wanted to find the crossing location here. And so what I did is I took, let's see, how was I thinking about this?
We can just take the shear value divided by the slope.
That's what I did, yeah. So 18, so that point, I've got 18.0078 that needs to be removed essentially at a rate of 20 kilonewtons per meter, because this is kilonewtons, so that goes away, we just get meters. That gave me 0.9004 meters. but that distance is just this distance here, right? So the actual position here would be 1 plus 1 is 2 plus 0.9. It's almost 3 meters. So that point comes out, let me just erase this bit. So that point comes out to x equal 2.9004 meters. That's where the crossing occurs. The next thing to do is to make the moment diagram. That would be in kilonewton meters. And let me plan ahead a little bit here. So I'm going to need 2 points. Let me start this one at the beginning at A. Now there's no moment at A, that's 0. And so really all I need to do is add up area as we go. So 8.8953 times 1 is going to be 8.8953 kilonewton meters. So that's pretty straightforward. We'll do that math in our heads. So this point at B is 8.8953. And then all we have to do is add up negative area. So negative 16.1047 times 1 is the same number. So we basically have to subtract 16.1047 from 8.893 to get our next point at C. And when I did that, I got negative 7.2094. So that's what that looked like. And then there's a distributed load in the beam, and so the shear decreases as we move along. Okay, it doesn't remain constant like it has so far. So what I realize is that since we're adding a lot of area at the beginning, that the change from this point is going to be greater near C and smaller as we move towards this point, which is intermediate between C and D at the crossing. And so I just drew a concave down curve to get us to that point where crossing occurs. Let me make some notes here. Let's say this is D. We'll mark off some points. There's A, B, C, D. And then the crossing occurred somewhere over here. So I just put a point like that and drew a concave down curve like that. And to calculate the magnitude here, all we need to do is add up this area. So really it's that dimension 0.9004 meters multiplied by 18.0078 and then divided by 2 because it's a triangle. Okay, so that delta, whatever that came out to be, I don't remember, but this point up here, that would be the change from negative 7.2. You just add whatever the area of that triangle is. Now bring you up to this point. I got 0.8976 kilonewton meters for that point. And then the area of this little triangle down here, negative 5.9922 multiplied by what? About 0.3 meters, right? Because it's about 0.9. So about 0.3 times that. Took care of the rest of that and brought me back down to 0. Now there's another crossing here of interest. And so how did I do this? Let me write down what I've got here. I don't remember how I thought this through, but we'll discover it as we go. 1.2 minus 2 times 0.2996 equals 0.6008, and so the position is 2.6008. So what was I thinking here? I don't remember. We'll have to think through it quickly. Let's see. The 1.2 would be this dimension, and so this must be, let's see, 1.2 is from C to D. I don't know how I was thinking of that. Oh, I know. There are two lengths here. This was symmetrical because the triangle has the same slope on both sides. So since it was symmetrical on both sides, I knew that this shape was, I haven't drawn it well, but it's symmetrical, and so there's two lengths here. That's what that 2 is for. Somehow I knew that this distance was 0.2996. How did I figure that out? I must have typed it into my calculator, and I don't remember how I did that.
Well, you just subtract that from the 1 point, well, you just take the 0.9004 to subtract it from 1.2 to get your remaining distance.
Well, that would be half of the curve above the.
Right, yeah, you're right, because since this is symmetrical, you're right, that's what I did. Because I know the distance from here to here is 0.9004. So that's how I came up with with this.
Yeah.
Thank you. But still, how did I get 1.2 in that? I'm not convinced that that's right. Let's do it, let's think it through. Since that's symmetrical, and we know that this point, see, since this has a slope of 0, we know that's this point, because this graph, the shear, always tells us the slope of the moment. So we know that this point and this point are the same. So the distance from C to here would be 0.9004, right? Because remember, these two are the same distance as these two, okay?
So then you get the area, or the length to the right, if you take the 1.2
Right.
minus the 0.004.
So that must be where I got the 0.2994. Yeah, so 1.2, is that what you get if you subtract?
0.2996.
Yeah.
Yep.
Okay, all right, so that's where it came from. So then this is 0.2996. Yeah, well, of course, that makes sense. Yeah, so that'll give us the 1.2. So then,
So then if you
so then I calculated this distance and, well, wait a second, then X is not, this would not be right. The position would not be 2.6008. The 0.6008, no, it would be, it would be. I'm getting all confused here. Yeah, because I multiplied 2 by this, so I've got this distance right here, minus, from the 1.2 would give me that distance. Okay, so that's right. So I use symmetry to figure it out, basically. I see confused looks.
I'm not getting that.
Okay, all right, well, let's go through it. Let's start at the beginning, and grab your calculator and just run through it, and then you'll see how it works. Let's get rid of all this. Do you agree with this?
Yeah.
Okay. So then, can't we calculate this distance pretty easily?
Yeah.
Let's do it. 1.2 less 0.9004 is what?
0.2996.
Right. Okay. And so now let's calculate this distance. It's going to be 2 times that.
Okay.
Right. So what number is that? That would be 0.5992.
0.5992.
Okay. So then if we are interested in this distance, then all we have to do is take the original length, 1.2 meters, subtract off the 0.5992, okay, right? And that should be the 0.6, what was it, 008 or something?
Yes. So 0.8.
And then if I want that measured from back here, add 2 meters, we were done. So I cheated a little bit, I used symmetry. That way I didn't have to come up with an equation for this slope and actually perform the integration. But since we're doing it on the video,
Yeah.
I've got a captive audience, do you mind if we do that too?
Let's do it.
Let's do that, because that would be good. All right, so the shear equation here, we're gonna have a slope, an mx plus b, right? So that's pretty straightforward. So the slope is gonna be a negative slope. The change overall, is gonna be, am I thinking right, 20 kilonewton meters times 1.2 meters? Is that the overall, yeah, that would be the overall change.
So that'd be 24.
24, yeah, you're right. That would be 24.
All right, we multiply by dividing.
Well, I'm multiplying, because I got 1.2 meters worth of 20 kilonewtons per meter.
So this could be a rise of negative 23.9998.
So
24, right, because going from the original numbers. So negative 24, and then the run is 1.2 meters. Okay, let's put units in here just to make sure things come out right. And so that would be times x plus some constant c. Well, we know that we want the shear, let's just use round numbers so our life's easier. Okay, let's call this 18. Okay, we know we want the shear to come out to 18 kilonewtons when we're at a position of 2 meters. So if you plug in x equals 2, in fact, here let's see, what can we do? We can get rid of this bit. All right, so we know that the shear is 18 when x is, we could have just written it down, 20 kilonewtons per meter. When x is 2. But we need a constant to make this work, right? So all I'm doing is finding the intercept. So that'd be negative 40, so the constant is 58, right? So that takes care of the constant. And so now when we plug in an x position of, I've erased my figure now, what? 2 plus 1.2, 3.2. So plug 3.2 in here, and let's see what we get. Let me change this. We should get -6.
Yes.
Okay, so we got negative, so now we know our shear equation represents that line like we want it to. Okay, good. So now we need to integrate, in order to find the equation of this line, what we're going to do is realize that the moment as a function of position is just the integral of the shear as a function of position, getting ahead of myself, plus some constant, okay? So now let's perform that integration. Let's see our plug in. 0 to x, v of x is negative 20x plus 58 dx plus some constant, and I'm sorry I'm out of space. I don't want to erase that diagram yet, so I'm going to keep going back and forth. If you're on the video, I apologize ahead of time, but you can pause. So let's see, this would be the moment as a function of x, and I'll try to leave myself enough space. So moment as a function of x, then if I integrate this, it's going to be negative 20x squared over 2. Integrate this plus 58x, and let's see, plus a constant. Yeah, that should be it. And so now all I have to do is make the moment equation match what's over there, and we should be okay. Since this this equation should end up working for the whole curve, so we'll verify it and see if it works, but it should work for all of them. So if we plug in a position of 2 meters into this, we should get a moment of negative 7.20, is that 99? Let me get my sheet. No, 7.2094. Okay, so what that means is we get negative 7.2094 when we plug in, well, let me simplify this, because negative 20 over 2 is just negative 10. When we plug in an x position of 2 meters, right? Because all I'm doing is plugging in this point right here, C. So plus 58 times 2 meters plus some constant C. So just tell me what that constant is, if you would, guys.
No, 103.2?
I don't know.
Oh, you right by?
That looks right, yeah.
3.2?
No, I'm not getting that.
No? Okay.
That's,
Let's see, I'll do it over here on calculator. Pretty straightforward. We're gonna have to move these terms to the other side, right?
right.
So we're gonna have, it's gonna be a fairly large negative number, because this is the biggest term. 2 times 58 would be 114, so 114, let me, minus the 7 point,
Double checked it.
I got a negative 83.29.
4.
Did you square the 2?
Yes.
Ah, you're right, I didn't write that here, did I? That's my fault. So, so the 2 squared before, that'd be 40, which is added to the other side, so plus, so I got negative 81.2094, does that agree?
Well, I got that negative 83.29.
83?
Yeah.
Well, I'm not happy, I'm gonna try it again. Shouldn't be that difficult. Let's see, I'll rely on the calculator.
I don't want to mess up. I put 2904 instead of 2094.
Okay, all right. Well, I've erased my answer, so let me do it again. 7.2094 plus 40, if I can do that much math in my head. Well, now I'm getting negative 83. Try it again.
I mean, I know the dots negative too. Yeah, we both got negative 83.
Okay, all right, yeah, I did that time as well, so I made a mistake before too. All right, so the constant is, you say negative 83?
Yep.
0.2094?
2094?
Yes.
Okay, so now we should be able to verify this. Let me simplify this as well. Let's get rid of that 20 and make it a -10. Should make our life easier. So there's our equation for the shear as a function of x. Now we should be able to plug in a position of 0.6008 and get a 0 out of the equation, right?
Okay.
So let's try plugging in, let's try plugging in 0.6008.
What would that be?
In there.
Wouldn't that be 2.608?
You're right, I'm sorry. That would be 2.6008, you're right, because that's the position of it. What do we not need anymore? Need that. Need that.
Somewhere must have, like, it's just rounding error, but I got a -0.0046.
Okay, so 2 zeros, I'm happy with that. Let's plug in a couple other points though. We could plug in 2.9004. And we could plug in the last point of 3.2 meters. And 3.2 should give you a 0, the 2.9004 should give you that maximum of whatever the moment is there. I've erased it. The magnitude of the moment was, put my sheet over here. Let's get rid of all these dimensions because we don't really need them anymore. The magnitude of the moment here was 0.8976. Able to verify either of those numbers?
Pretty close.
Both of them were.
The 2 zeros.
I'm sorry? Verify the zeros? Okay. Did either of you verify this point?
I did, I got 0.895, or 891.
891, okay, that's within reason, makes sense. All right, I think that's it. Is there anything else we should do with this problem? We've got the equation of the shear, the equation for the moment, which of course is valid from 2 meters all the way out to 3.2 meters, we just discovered that. And I think that's about it. All right.